Welcome back. We'll continue the discussion on this structural analysis. So we have looked at the static beam equation, and then also looked at how the for constant loading and distributed loading for cantilever beam, how that acts, and then tried to estimate the bending moments at the root. So essentially, from or using the basic structural mechanics equation, we have mm, kind of tried to correlate with the forces on the blade roots and that. Now, what we will continue is the oscillations and eigenmode. Okay, so essentially the vibration part. So oscillations and eigenmodes. So this essentially the vibration of the body that we would like to continue to. Obviously here, while talking about that, first thing that we'll introduce the spring mass damper system. So the spring mass damper system will first introduce, which is essentially a simple kind of a this is mass, and this is where the force is applied. This is how, when the spring is exposed to a external force, so then and the force is related, the body actually oscillates. This typical fundamental vibrational analysis, so they follow simple equation where mx double dot plus beta x dot plus kappa x equals to f of t. So that's a, so essentially with time the force which is applied, and here the few things that is x is uh, displacement m would be mass, f of t is external force, k of x is spring force, beta is damping parameter, so which could be viscous damping or linear damping. So you have all these parameters for the analysis. What one can now, so once we find out the solution for this particular system, and then from there we can again try to correlate with our rotor system and their, so how we can go about it. So let's say for f of t, which is given at f naught e to the power j omega t, where f naught greater than 0, and usually we take the real part of the design, a real part of the solution and design. Okay, so now the solution can be written. So here the solution, which can be written as xt x naught j omega t, okay, where x naught belongs to complex. Then x dot is j omega e to the power j omega t, and you have x double dot minus omega square j omega t. Now if we put that back in that basic equation of spring mass damper system of this equation, so what we have is that m x naught e to the power j omega t plus beta j omega e to the power j omega t kappa x naught j omega t f naught j omega t. So what we can write, x naught k minus m omega square j beta omega equals to f naught. So this portion is the real part of the solution. This is imaginary part of the solution. So here x naught is a complex number. X naught is an complex number with magnitude of x naught would be f naught root over of k minus omega square beta square omega square. So if we try to take the maximum x naught, that is maximum x naught magnitude is approximately taken at neutral resonant, which is eigen frequency omega nr, and we can say that k minus m n square equals to 0. Omega nr is root over kappa by m. So that is what you get for this. Now the question is that how much this f naught can be amplified. Okay, so we can say that how much can f naught be amplified. So our spring force, which is F naught spring is K into X. So what we have, magnitude of F naught spring is K magnitude of X naught, which is F naught by 1 minus omega by omega inner square plus beta square by K square omega square. So what we get, let's say at omega is omega nr, we get F naught spring K by beta omega nr. So this clearly tells one thing: smaller the damping, the higher is the amplification. Okay. So if you can like plot this, let's say omega, let's say this is omega nr, this is F naught spring by F naught, this is K by beta omega nr. Okay, and this is 1. This is known as Bode diagram of F naught spring of omega divided by F naught. So typically the amplification factor can be 5 to 10. So amplification factor can be 5 to 10. So the resonance shall typically be avoided. So resonance shall typically be avoided. Now at very low frequencies, spring force equals applied force. That is our static analysis is sufficient. So which you can correlate that how this resonance and amplifications are connected, and that can be avoided, and where your static analysis is sufficient to estimate back this. So where we are heading with this particular thing is that, so this is kind of giving you an idea about that the simple spring mass damper system that you have, and their oscillations and oscillations frequencies you can estimate. And once you can estimate that, then we'll use this information or the similar way to correlate when the turbine blades exposed to this kind of vibration. So that is the whole idea, that how we correlate these natural frequencies or eigenmodes and all these things. Uh, so this gives our the oscillation frequency or eigenfrequency, a natural eigenfrequency. Now we can find out the eigenmodes and that. Okay. So now we look at eigenmodes. Okay. Now for spring mass damper system with more than 1 degree of freedom. So we can have the displacement, which can be, so the displacement would be represented as vector, let's say WT, which belongs to Rn. And the equation of motion becomes mw dot dw dot kw equals to f of t. So the previous analysis of spring mass damper system, we had 1 degrees of freedom. So essentially, if you try to schematically draw that, then now here in this equation, what we have, M is an mass matrix which belongs to R n by n. D belongs to damping matrix. K belongs to stiffness matrix with n by n. Now, what if damping is neglected? That is D0. Then natural resonances must satisfy that Rn. So what we have in the solution vector Wt W e to the power omega t, and we have m w double dot plus k w equals to 0. And what we can write, m equals to 0, m inverse k minus omega square I is 0. So this is an eigenvalue. So this is an eigenvalue equation. So eigenvalue equation for matrix m inverse kappa n by n, and we know there are n eigenvalues with n eigenvectors, which is essentially eigenmodes. Now here, interestingly, since these are now we are dealing with a metric system, so as both m and k are positive definite eigenvalues of n inverse k are real and positive. So what we are interested is we are often only interested in the eigenmodes with lowest eigenfrequency. Okay, so this is what we are essentially. Now the thing is that once you get the eigenmodes, how you can estimate the solution of this. So the point here is that in multiple degrees of freedom case, we are dealing with a metric system. And from the metric system, we try to find out the solution. Okay. So now how we find out the solution? So there is a method called Rayleigh method. So we use that. Let's say Rayleigh's method. Okay. Obviously, we have a good guess of an eigenmode vector is W bar Rn. Now to find the corresponding omega square, so we have to find the corresponding omega square we can use the equation which is k w bar omega square mw bar. Now, let's say uh, this could be over determined if w bar is fixed. Okay. Uh, then we can multiply by half of w bar transport, and that gives that half of w bar transport k w bar is omega square half of w bar transpose m w bar. So this system here, this is overdetermined if that vector w bar is fixed. Then we can multiply by this half of w bar transpose, which gives us this. Now, this component is essentially nothing but elastic or potential energy at maximum displacement, and this is kinetic energy at max speed, which is zero displacement. So from here, what we can get at omega is half of w bar transpose k w bar divided by half of w bar transpose m w bar. I mean, one has to be careful that you cannot cancel this numerator and denominator here. You cannot cancel this numerator and denominator because you are dealing with matrix here. You are not dealing with scalar anymore. So these are kind of an vector. So what it gives you that if the guess of W bar is good, the method is surprisingly. So what we can say that, let's say if the guess of W bar is good, the can give surprisingly accurate estimation of omega. So that's what it does. So essentially, again, just to point to note here, when you try to find out this omega, you cannot cancel each other out because you are dealing with the matrix. So all depends on this, that the what is the, because we started with the guess of the eigenvector w bar, the vector eigenvector w bar for the guess values. So if the guess is good, this particular method of Raleigh method of analysis gives you a very good result. Okay. So we can also look at the error of this method and other things, and then try to extend for different example. Okay. We'll continue that discussion in other session.